All right. My name is Andre Masella. I'm one of the developers here at OICR in the Genome Sequence Informatics group. I would like to start off by thanking Heather for doing my makeup and Morgan for providing me with pentagram tape. So we begin summoning. Hands up, everyone, and repeat after me. Hail to the method of the inner class.
Hail to the method of the inner class.
We invoke thee.
We invoke thee.
All right. So we're going to talk about CallSites, and to do that, we're going to talk about those in not Java because it's easier to start with something that isn't as complicated as Java. Then we're going to talk about the invocation bytecodes that already existed in Java, putting a non-Java language on the JVM, what INVOKE Dynamic is and why you'd want it, the Bootstrap method, which is part of what INVOKE Dynamic requires, how Java optimization works, and a little bit about the debugger, and then we'll go back to some use of this in Java itself. So let's say we're in C, and I have a function f that takes a long and returns an int, and somewhere else I go and I call that function in the context where I'm passing in an int, and I'm expecting the result to be a double. When the C compiler generates the assembly code for that, it's going to have to correct the types of the arguments. In this case, it's going to have to do a widening operation, take that int and turn it into a long. It's going to have to put that value somewhere where the function being called is going to be able to access it in memory, actually call the function. It's going to have to get the result from wherever that function put it and convert that from, in this case, an int to a double, because we have another conversion on the return. So all of that assembly code we're going to call the call site. The actual mechanics of how this works depends particularly on your CPU architecture and the standard that you're using and yada yada. So the how we don't care. We just know that there's this block of assembly code that does a bunch of things. It's not simply a question of like jump into the function. If you start using C though, there are other kinds of functions, sort of. There are function pointers. So when you call a function pointer, you have to generate a different kind of call site. The call instruction that you'd use for a regular function is not the same as the one you'd use for a function pointer. All the argument conversion and return conversion would be the same though. C also supports variadic functions, functions that take a ... So the compiler has to generate a whole bunch of code to take all of those arguments, pack them in a way that the receiving function can deal with them. And you can have pointers to functions that take variadic arguments, so now you get to do both of those things. So C would have about 4 different call sites. If we upgraded to C++, then you get all of that and more, because you're going to need to be able to do method calls. And so there's going to have to be this, well, you know, which derived class am I actually calling? Go figure out what is the actual concrete implementation I have to call. The C++ language for that is called a vtable lookup, virtual table lookup. C++, you now have constructors, which are also kind of functions and need their own kind of call sites, and they're even more complicated. C++ also allows you to throw in exceptions, and the exception type handling is very complicated. So now you've taken all of this and doubled it for the exception versus non-exception handling functions. So it's up to the compiler to figure out what the right call site is that it has to generate for each of these different situations where you just seem to call a function. So one language can produce multiple different kinds of call sites. The types of the parameters may decide what kind of function it is. You can imagine if you've got a generic versus non-generic kind of world, that may be something you care about. The program flow matters. What kind of returns do you do? So exceptions are some kind of non-direct return that you have to handle. Some languages support things like tail calls, where you can return another function's value, so you don't need to be on the stack anymore, and you can do that forever. Some functions don't return. Exit in C, you know, that exits your program. There's no return value from that. That can be a different kind of call site potentially. The context matters. So calling methods is different from calling a static function because there's this, and that has to go somewhere. That has to be handled somehow. And different languages themselves are going to need different kinds of call sites. So some might be similar, like a Java method and a C# method are kind of very similar because the languages are very similar and the types of things they handle are very similar. So you can probably create something that could handle both of them. But that could be very different. I mean, something like C++ versus something like Lisp, those call sites are going to be potentially weirdly different. And when you build a virtual machine for a language, you generally build that virtual machine around what the calling semantics are that you need for that language. So in Java, Java was designed by people who loathed C++ and the complexity of C++. So huge parts of Java, like the no operator overloading, are reactions to C++. And so Java has very few call sites. And in particular, so Java also supports ... arguments. Those aren't part of the function itself. They don't generate a different call site. All the compiler does is pack all of those arguments into an array and then pass the array in. It's just syntactic sugar. The generic types are erased. So there are no actual generic types at the point where you're generating a call site. They've disappeared. Everything has been replaced with a reified type in the Java terminology. That means a lower type, so something like object, potentially something else depending on what you need. Exceptions in the JVM are erased. So interestingly, in Java, there's this idea between checked exceptions and runtime exceptions. The JVM does not care. When you define a method in Java bytecode, you include the exceptions, but that is purely for the Java compiler to be able to do anything with them. The JVM immediately throws that information away. It does not care. It rebuilds all of the exception information as it needs it. Actually doing the virtual method resolution is part of the JVM's job. So the vtable lookup of C++ is baked into the JVM. Overload resolution is the compiler's job. So if you have two methods that have the same name and different parameters, the compiler has to pick which one it's going to generate, and it writes a different bytecode for those two situations. Figuring out superclass conversion is the JVM's job. So if you have a function that takes an object and you pass it, a string, the JVM is the one that figures out, yeah, a string is an object. It's fine. Nothing's going to explode. Doing any numeric conversion is the compiler's job. So if there needs to be widening, narrowing, or changing from float to integer types, the compiler has to do that. So every method in the JVM is defined by three things: the class that it lives in, the method name, and the descriptor. That is the type of the arguments and the return type. And I will show you those. So the JVM has four different invoke bytecodes that allow it to call a method. Invoke static, which is for calling a static method. Invoke virtual, which is for calling pretty much any method on an object. Invoke interface, which is almost exactly like invoke virtual, except the type of this is an interface rather than an object. These are confusingly almost the same, and it's sort of a weird quirk of how the JVM is implemented that they are different, but we're going with it. And then invoke special, which is used primarily to call constructors. The name of a constructor is always bracket init, or angle init, close angle. So it's a name that you could never type in as a proper method name. All right, so let's look at some examples. So let's say we wanted to call string format. We would generate a bytecode that is invoke static. The name of the class, you'll notice that all the dots have been substituted for slashes. It is a weird quirk of how the JVM works internally that this is called the internal name of a class. The method we're going to call, format, and then the descriptor. So the descriptor for a method starts with an open bracket, because these are going to be our parameters. L says, I'm going to give you a class name, so we take a string, and then a semicolon means that's the end of that class name. Open bracket means an array of objects, and then I'm going to, there's no matching close bracket, just because. and then the return is a string. We can do something like invoke interface on char sequence length. This takes no arguments and returns an integer. Invoke virtual on atomic reference. We call set. It takes an object and returns void, returns nothing. Let's say we want to create a string builder. We first have a new bytecode to create an instance of that class. We duplicate it because the constructor is going to eat it and we still want to have a reference to it when we're done. And then we call invoke special to call the constructor that takes no arguments and returns nothing. So you can kind of ignore the surrounding bytecode. All we really care about is the invoke examples. So those are some standard Java. These have been around since Java 1.0 kind of invocations. So with only the bytecodes available, the Java system works on a stack of arguments that get mashed around and put into functions and returned from functions. So from that, the bytecode verifier, with just the bytecode, doesn't have to know any of the classes. It can tell whether the stack is correct. And with all the jumps, it can figure out what's going on. Once it has actually been loaded into the JVM and all the classes are loaded, it can do all the subtype checking to make sure that we're always converting classes in a way that's valid. It can also check that the target method exists, and it can also check the security level on that method. So you're not allowed to call a private method of a different class. So the compiler has already done the overload resolution and picked which overload it wants, and it effectively does that by the descriptor. There can be only one correct descriptor that matches a particular method. So if this was, taking in a particular type, it says, no, I want the object version of this. If you pass this an integer, it would be like, oh, okay, I'll convert the integer to an object, and then that java-lang object I will put, or that java-lang integer I will put in as java-lang object. And these were the only things that were allowed until Java 7 when INVOKE Dynamic happened. So let's go off on a side track. Let's say we want to build a JavaScript compiler that works on the JVM. I mean, it's Java in the name. Close enough. So obviously we're going to have to write some library stuff. We're going to need a JavaScript lang array that does the JavaScript array nonsense, and we're going to need a JavaScript lang object and all the encode URI and whatever else is in the JavaScript standard library. Okay, so we start writing our compiler. Well, arithmetic is going to be pretty easy. I mean, floating point arithmetic is floating point arithmetic, so whatever the JVM does, it will be fine. Loops, switch statements, if statements, that's easy. I mean, if you're really desperate for how this is implemented, write it in Java, decompile it, and then copy. Casting is going to be hard, but that's just because JavaScript casting is hard. That's not Java's fault. So figure out all the correct coercions, but there's a spec for JavaScript, right? Allegedly? All right, fine. But okay, then we need to write a function call. How do we do that? Let's try it and see why this doesn't work. So let's say we've got some JavaScript that looks like this. We have a function f, and it just takes a single argument x, multiplies it by 3, and returns it. And somewhere else in the system, we just call f with 7, and we stuff that into a variable somewhere. So our function for the bytecode we're going to generate, and I've omitted the class because I don't really care what class this is going in. We're looking at just the method. So we want it to take a double, and it's going to return a double. So we load our double argument, we load 3 as a constant, we do our multiplication, and we return that value. When we want to invoke this function, then we load our constant 7, and we invoke it on that method. That seems easy enough. Except, what if the function is an argument? Because, okay, I load the function, then I load my constant 7, and then what method do I invoke on it? Because if there's going to be a double-to-double method, then everything that is a that extends like JavaScript lang function has to have a double-to-double method, which means I would have to create all possible method argument types for all possible functions created in JavaScript, which sounds like a really bad time. And 99% of them are going to be not used. Well, I guess it's an infinite set. So an infinite number of them are going to be not used. Okay, we can get around this. Same original code, but what we're going to do is, rather than take a double, we will take an object and we will return an object. And so we will load that object, we will cast it to a double wrapper, we will unwrap it to get the original value, load our constant, do the multiplication, convert it back to a wrapper, and then return the wrapped version. And then we want to call it, we take our constant, we wrap it, and we do the invoke on the wrapped version. So okay, we have some extra steps, but that works, right? Except you can call functions with the wrong number of arguments in JavaScript. So, and to make matters worse, if I take a function, even if I don't actually consume the argument, even if the argument isn't named, I can still get to it through JavaScript's arguments expression. So I can't just throw away extra arguments, even if I wanted to, because they're still sort of visible. Now, I know what you're thinking. You're thinking, well, JavaScript sucks. Who cares? This is totally a JavaScript problem. PHP has the same thing. Yeah, PHP is not, no, okay. Python has the same thing. You can access the arguments as a list or as a dictionary using args and quargs. Ruby has the same thing. Lisp takes variable numbers of arguments and lets you do partial application. So if you have a function that takes 3 arguments, you can just give it 2 and then you get a function returned. That's going to be a good time. So the best universal solution that you can come up with is every time you want to call a function, you create an array, pack all the arguments into an array of objects, and let the callee deal with it. That does work, and that's what a variety of languages on the JVM were doing early on. It's really slow. It involves a lot more of that wrapping and unwrapping and a lot of runtime type checks. So we could do better if we were at runtime. The way you could do that is to use reflection to find the best match method, convert the parameter types as necessary, invoke the method using reflection, and then convert the return type. The problem with that is reflection is really, really slow. I'll talk about why it's really, really slow later. And actually, if you've used Spring, this is what it does. Whenever you use a method interceptor, this is exactly what it does. So if you wonder why Spring is slow, I have an answer. The other problem is we have to figure out this every call. It would be really nice if we could cache the procedure, because we know the procedure is going to be the same the next time we make the call. And there's no real way to do that until INVOKE Dynamic. So what if we could figure it out at runtime and cache the procedure? So we'd need 3 things to make that work. The JVM would have to have an instruction to do our special kind of call, that is INVOKE Dynamic. It's going to have to provide something that figures out this mess and decides what to do. That's something that you provide called the Bootstrap Method. And we need a better kind of reflection. So INVOKE Dynamic itself takes 3 things: a method name, a descriptor, so that the verifier still works, and a bootstrap method. And we'll talk about the bootstrap method later. So if we were generating our call in JavaScript, we would load wherever the hell f lives, load our constant 7, and then create an INVOKE Dynamic that says, okay, for our bootstrap method, we want to run some JavaScript method. It takes a JavaScript function and a double, and it is going to return us an object. That is what I need you to do, make it happen. All right, we're going to need something better than reflection. The biggest problem with reflection is that the JVM has this whole security model, right? I have private methods, I have private fields, you can't touch them until you have reflection, in which case you can just go and change the permissions on a field and do whatever you like to it. So the Java team a while back created an idea they call a mirror, which is possibly one of the worst puns I've had in a while because a mirror is a thing you use for reflection. Yeah, all right. The thing about mirrors is there is one reflection API that everyone uses. With mirrors, you create multiple instances, and each mirror can see different things. So if I create a mirror in a class, I can see my private fields, but if you create a mirror in your class, you can't see my private fields. They're not part of your mirror. They're not in the reflection. So the method handles lookup is the mirror API. When you create one, it has the visibility of its creator, and one is created automatically whenever you do an invoke dynamic, so that you just get it in the context that it was called. And with the mirror, you can then find methods, fields, and you can actually convert fields into a function that takes a getter, basically a getter or a setter function. You can generate those automatically using the mirror. You can also grab constructors. And when you take one of these things, you get a method handle. It is some reference to a method with all of that information embedded in it. The greatest thing about method handles is there's a whole set of APIs for converting one kind of method handle into another. So if you have a method handle that, say, takes a double and you want it to take an object, you can transmute that method handle from one type to another, and it adds the boxing for you. So there's a whole, if you go into the method handles class, there's a whole collection of methods there to help you manipulate method handles. You can put in constants for parameters. You can get rid of arguments. So like you can build an argument that's like, I have a function that takes one argument, produce me a function that takes two arguments and just throws the second one away, or throws the first one away, depending on what you need. You can rearrange the order of the parameters. You can apply an arbitrary transformation to each one. There are spreading and collecting ones that let you take an array of things and convert it to arguments, or convert arguments into an array. You can fold arguments. So if you have some kind of, sum these arguments, that's the thing you can do. And you can add in guards. So if you need to add some kind of like, yes, it's a double, but it has to be, greater than 5, or throw an exception, you can create a method handle like that. You can create method handles either by rummaging in a mirror. There's also a public mirror. So if you go to method handles, there's a public lookup that is, it can only see the public methods of everything. It exists in no package. It has no private access whatsoever. You can also just create a method handle that returns a constant, or create a method handle that throws an exception, or one that returns a parameter, basically an identity method handle. So you can imagine if you've got one kind of call site that you need, and you've got something that's close, you can possibly manipulate it the way to the thing that you need. So that is what the Bootstrap method does. It gets a mirror to the caller. It gets told what the call site type is like, what the thing is expecting, and then it basically says, return to me the new bytecode you would like me to put in that place. So you create a call site object. There are 3 different kinds. A static call site is basically, here's the method, I have made up my mind, this is it, we're done here, have a nice day, don't ever talk to me again. There's a mutable one where it's like, here's this method, but I might change my mind later. And then there's a volatile one, which is even more so, I'm going to change my mind often. You can create subclasses of these call sites if you want. So the JavaScript Nashorn engine does this. So a lot of times what it will do is it will say, I might do this kind of thing the first time you run, and then if you supply me with a different function under these situations, I'm going to reoptimize the Java and the JavaScript code, and let me give you another method. I'm going to change my mind later. And the Bootstrap method is, regular Java code, so you can do whatever you need in there. You can reinvoke the compiler, generate new bytecode, load it into the JVM, take a method handle from the generated code you've just created and say, I want you to do this now. Wow. Yeah. So let's talk about why the JVM doesn't suck anymore. Has anyone used Java from like that era? Was it awful?
Yes.
Was it slow?
Yes.
Was it really slow?
Yes.
Like painfully slow?
Worse.
Like you waited like an hour for a Swing application to load, kind of slow? Yeah. The reason is that the JVM pre 1.2 and before was not very smart and basically interpreted the Java code as it was written, or the Java bytecode as it was written. And in Java 1.3, Sun bought a company and took their code to produce Hotspot, the JVM that we are now using. And Hotspot has an incredible ability to optimize. And it does a bunch of things that make the optimizations compound in the value. So one of the things is the optimization is iterative. It's named Hotspot because it tries to figure out which parts of the code are getting the most activity, the hotspots, and then it does more aggressive optimizations on those paths in the code. And then whenever it does an optimization, it puts little counters in the code. And so it occasionally checks in and says, oh, are you busy? If you're a busy part of code, I should come back to you and try to see if I can do something better. One of the optimizations it does is inlining. So when it calls a method, it brings the body of that method into the caller as a way of making it faster. And that makes the other optimizations work better. So the optimization path kind of looks like remove the invoke instruction and replace it with the bytecode for that method, optimize the new conjoined method, and then repeat. So even if you've got layers of methods calling methods, it can optimize across all of those method boundaries, which is why getters and setters, the fact that they are method, don't worry about it. They're deleted almost immediately by Hotspot. It realizes they do nothing and just pulls their contents in. So as an example, this is not actually how Hotspot works, but conceptually, say we have a method x that checks whether a value is 0 or greater than or equal to 0. If it does, it converts it to a string. Otherwise, it says no. And I have a function called y that calls x with an int argument times itself. It will get optimized, or it will get inlined so that it is now doing both of those things at once. And now the optimizer says, hey, v times v is always greater than equal to 0. So I can just do dead code elimination, get rid of the branch, and now this thing just becomes convert the string argument, or convert the argument to a string using that method. Of course, the next step will be, and then that method gets inlined. And it can just iteratively do this again and again and again to make it better. The optimizer can actually get rid of whole objects. When you do something like you create a string builder, and in one method you append a bunch of things and then convert it to a string, it doesn't actually do that anymore. It slits the string builder open, rips out its fields, makes them local variables, does the optimization. It slits open the new string constructor, which would copy the array, says, the array isn't going to be used anymore. I can just remove the copy and make it a move, and just returns the array that it created. It can figure out constant expressions. It has all kinds of amazing optimizations that it can do that sort of work in this combined manner. Once it's done, it produces assembly code for the CPU that looks nothing like your original code. Until you hit pause in the debugger. And then it has this complicated dance where it reconstructs all the objects it lied about. Or if you throw an exception, because then it has to recreate the call stack. Which means if you throw an exception just to look at the name of your caller, you're a bad person. So reflection is slow in part because when reflection happens, that has to happen in the C++ part of Hotspot. It's actually part of the C++ code that is Hotspot. And once you go in there, the inliner can't cross that boundary. So every time you call reflection, you are putting in a barrier to the optimizer that it can't cross. And that's also why Spring is slow. Every layer that you have in a Spring application becomes an impenetrable barrier for the optimizer. It has to happen all at once, completely synthesize the result, pass it through the C++ code, and then back into JVM land on the other side. And I know why Java's fast. So you might have the question at this point, oh God, why are we doing all this complexity? Well, the Bootstrap method is just JVM bytecode, and the call site is just JVM bytecode, and the caller is just using JVM bytecode, which means that the inliner still works because we are not going into any of the C++ parts of Hotspot. That means the JVM compiler, the JVM can basically inline the compiler into your code. If your Bootstrap method is, write some new bytecode, it can just inline that. I know, right? The level of optimization that it can do in this situation is huge, which is where all the performance benefits from doing this come from. So yes, we kind of have to jump through a bunch of hoops to get there, but there's a big benefit to doing so. Okay, let's go talk about Java and its sadness. So INVOKE Dynamic was added to the Java virtual machine not for Java. It was added for supporting non-Java languages on the JVM. That means it came in Java 7, and Java 7 didn't use it at all. Java 8 uses it to make lambdas. When you do lambdas and method references, those actually generate INVOKE Dynamic instructions. It does that through the LambdaMetafactory, which I'll go into a little more detail on in a moment. Java 9 uses it to build better string concatenators. If that's not a sad enough use. There's going to be no new uses in Java 10. And also there is no way to actually generate an INVOKE Dynamic instruction directly. You can incidentally generate one as part of a lambda, but if you want to control what the Bootstrap method is, you can't do that in Java. You want to do that, go use some other language on the JVM. There have been proposals to put it in, but they keep getting shot down, so, maybe Java 11. So let's talk about LambdaMetafactory. So let's say we wrote some Java code like on the top. So we have a class with method foo that takes a string, and we want to return a consumer of strings through another function. So we return this : foo. What's going to happen is at the place where we actually do this : operation, it's going to create an INVOKE Dynamic instruction with the Bootstrap method, except as the method name. And this is going to take a foo, which is this, and is going to return a consumer, which is what we want. Yes? Are we okay? All right. The Bootstrap method is this gargantuan monstrosity at the bottom. So the Bootstrap method is an invoke static instruction because in LambdaMetafactory, there is a method called Metafactory, and it is responsible for figuring out what is going on. So let's ignore the arguments for a moment. It takes some arguments, and it's going to return a call site. Okay. So it has the ability to get 3 pieces of information from the INVOKE Dynamic instruction. The first one is lookup. That is the mirror, so it can go figure out what's happening. The next one is a string, which will be the name of this argument, in this case, accept. And then it will get a method type, which is the type of function it has to produce. It can also take extra arguments, and that is totally a implementation defined thing. It is whatever your particular situation needs. So the ones for LambdaMetafactory look like another method type, an invoke virtual instruction of the thing we actually want to call, and then another method type that is also the thing we want to call. The reasoning for this is this. So to create a consumer, I need to know the class that I'm going to produce if I want the Lambda. I need to know the method's name in that class that I'm going to be, or in that interface that I'm going to produce, right? So if I'm creating a consumer has one method called accept. It takes an object as an argument and it returns void. So it needs to know that information. And so now it has those three pieces of information, right? It knows consumer by the return type. This is the method in consumer that I'm trying to override, and here's its name. So now it knows what it's trying to get to. This is the function that it wants to use to call that. So that's all the information it needs there. And because of the way generic erasure works, it needs to know the non-erased version of this method, which is that. And from that, it will be able to figure out how to generate some code to do the Lambda. If we had this situation where there's an extra argument that gets captured from the outside, then most of this is the same, but now we're taking two arguments, right? We're taking the integer, or the long that we need, as well as a foo, and well, there's our long. Long is J in Java. Of course, because L was taken for object.
Right.
I don't make this shit up. Okay, so then the method that we're looking for in consumer doesn't change. We're looking for something that takes an object and returns nothing. We know that we now need a double as one of the arguments to the thing we are trying to get. And so this thing knows, okay, if you gave me a double that I didn't ask for, and the thing I have to call has a double that I didn't know I need to provide, let's just assume those are the same thing. And so it boxes up all of those arguments and passes it on. So it's capturing those arguments. And this is why, if you've ever gotten the thing you want must be final or effectively final as an error, it's because it has to copy it into the Lambda. So it can't have it change, because then what do you do? So how the LambdaMetafactory actually works is it finds the target method it sorts all of this, like what conversions do I need to do and that kind of thing. It actually creates a new class that implements the interface you want, creates a field in every class for every captured variable, puts in a call to the required, or creates the method that the interface needs to implement. It may create a second method called a bridge method, which is a whole mess of how Java deals with generics that I don't want to get into. It creates a constructor that takes the captured arguments. It stores them in the fields. It might do conversion if necessary. It then takes this whole class, loads it into the JVM, gets a reference to it, and then returns that as stuffs that constructor into the call site. So the call site becomes create a new instance of this class I just made that is as if you had written an inner class, but it does it at runtime. The advantage to that is it keeps a cache of these things. So if it generates the same one, it doesn't actually generate it, it just gets it from cache. So what other kinds of things you could do? Well, creating arrays in JVM bytecode is a pain, so create a method that does that. If you look in the Groovy source code, there is a class called arrays, which is 250 something methods that all just take all their arguments and put it in an array. because that's more efficient bytecode wise than actually creating an array of the right size and putting all the arguments in one at a time. You could create tuple classes automatically if you had a language that needed tuples. You could create anonymous classes with named fields like C# does, and the advantage to that would be is if you create two in two different parts of the code, you could have it automatically deduplicate them. You can do dynamic dispatch. So in Java, the dispatch overload resolution happens at compile time, right? If you give me something that is object, and there's a bunch of methods, there's foo int, foo long, foo string, foo object. The compiler says, okay, I have to call foo object. If you did a dynamic dispatch, you could have it say, well, what's its actual type? If it's actually an int, I'm going to call foo int and not foo object. You can have that happen at runtime. And multiple dispatch too, if you can do it with any combination of arguments. You could do something like generate RPC stubs automatically and have it figure that out for you. If you wanted to create memorized functions, so cache the return value, because if the arguments are the same, the return value will be the same. You can have it generate that for you. When you do things like regular expressions or format strings, it has to reparse those every time you do that. If you used INVOKE Dynamic cleverly, you could have it cache those so it would do that compilation of those strings only once. And that has the added advantage of those, now that they're deduplicated, become more hot, so Hotspot will optimize them better. You could do auto wiring if you're that kind of sick, twisted person. The only thing is you have to work in not Java. So who's actually using this? Well, Java 8 is now using this. Scala is using this. Some of it is in development. JRuby is using it, but is an optional compiler option, and it figures it out based on what JVM version you want to target. There is a JavaScript engine written by Oracle called Nashorn that is now delivered with Java 8 that makes heavy use of this. Groovy uses this. There are some popular JVM languages that aren't. Clojure claims they don't really need to bother with this. Kotlin says, we want to target old broken JVMs, so we can't use this feature. Java 1.5 on Android forever. That's their target market. And Jython doesn't, and they don't seem to have a good reason why.